Okay, welcome back to the continuation of the May 2009 Unit 1 AS Physics paper that we're looking at, and we got to question 15A, which I've been pulling up here on the screen and having a look at, and then comparing the answers on the mark schemes and seeing why certain answers which seem okay miss marks. It's very important to see the world a little bit from the perspective of the examiners, and therefore to maximize how you're answering so you can do as well as possible in these exams coming up. So let's have a look at the question before we look at the answers, and we talk about them a little bit before then. It says a student is asked to provide an explanation of why a bottle on a table remains stationary. It says complete a free body force diagram for the bottle, and they give you the bottle and you're supposed to draw something on there. So I can't draw on the PDF, so I'm going to draw myself a little bottle here. Hopefully most of you can that's a horrible bottle, but hopefully most of you can see that this is to do with Newton's second law, and if it's not accelerating, the bottle is not accelerating in any direction, it must mean that the forces are balanced. So from the center of gravity, I'll draw the more obvious force first, which is the weight. You have to label the force, and important is to do two things. One of them is to make sure that the other force is along the same line and has a roughly equal length, so you can have them smaller both or longer both, but don't have one longer than the other. And the next thing is here, this force is called the reaction from table, so the reaction force from the table. Okay, with those two labeled like that, you get the full marks. But let's have a look at what some people have answered to avoid making these mistakes in the future. First guy drew it like this, and look at his line of action of the forces. One is sideways, slightly the angle is off, and the other one is straight down. So the examiner notices this and says the response has correct labels, but the forces need to be along the same line of action to get the second mark. There's another answer here, a much better one. Problem is the labels that he's used. He's drawn the thing properly, but then he said push of the table on the bottle, which is correct. He should have written reaction really, but this one is push of the bottle on the table, and the free body diagram is for the bottle. It's not asking you for the forces on the table themselves. So what he's done here is he's drawn a Newton third law pair of forces, which are the same type of force, both contact forces on one object and the other. So the Newton's forces always act on different objects, and these two that he's written here are on different objects. But the exam question asks for a free body diagram for the bottle. So you on a free body diagram you will never see two Newton's three forces, because they would be acting on different objects. So what I'm saying here is, if this is my bottle, the forces acting on the bottle are 1, the contact force acting there, and 2, the weight acting there. Right, on the same line, and the weight is the pull by the earth, and the contact is the reaction is the contact force from the table, and they're both equal. But Newton's pair of forces would be different. Newton's pair acts on different objects. So those two on the left act on the bottle, but the Newton's pair act on different objects. One of them is the push of the bottle on the table, and the other one would be the corresponding push of the table on the bottle. That would be a Newton's pair. And then there would be another Newton's pair force here. So there's actually 4 forces acting, but we're only drawing 2 because we only care about the forces on the bottle. One of them would be the weight, in other words the attraction of the whole of the earth down here on the bottle and pulling it downwards, and the other one is, surprisingly maybe, but hopefully not, the attraction of the bottle on the whole earth. The whole earth is being pulled up towards the bottle by its own the same gravitational attraction. It's much more apparent in the bottle because the mass of the bottle is very small, so the acceleration, it would be huge. If you let it go, it speeds up very quickly, whilst the mass of the earth is huge, so its acceleration is very small. So that's a good intro and a bit of insight into the ideas of the free body diagrams. And the most important thing here is that all the forces in a free body diagram, if you have a guy who's diving or parachuting or whatever and he's falling, then make sure you drawing the forces acting on him, right? So if this is my guy parachuting, the forces are then air resistance going upwards and the weight going downwards, and the fight between these two is what determine his terminal velocity and so on. But those two forces are acting on him. Probably best way to draw them here would be to draw the weight from his center of gravity downwards and then to draw the other one from there. Okay. Hopefully that's a useful revision. Okay, so where are we? We did this one. Let's talk about the next question then. Part B says, student writes the following incorrect explanation. The force of gravity pulls the bottle down. The bottle pushes down on the table. So by Newton's first law, the table pushes up with an equal and opposite force. According to Newton's third law, if the forces are balanced, nothing can move. So we write the student's explanation correctly. That refers to just, that's lucky because I hadn't seen this, to the stuff that I was just talking about. You need to say three things, and we're just going to go straight to look at the answers because I've just explained the corrections that the student has there. The Newton's third law are forces acting on different objects, and he's mixing them here. Okay. First of all, Newton's third law does not say that if forces are balanced, nothing can move. The third law says that for every force there is a corresponding opposite which acts on a different object and is of equal magnitude and opposite direction. So that's one of the statements that he makes that is wrong. Another one is that if the force of gravity does pull the bottle down and the bottle pulls on the table, but the first law doesn't have anything to do with the fact that the table pushes up with an equal and opposite force. That's the third law. The first law would say that if it's not speedy, if it's not doesn't have any velocity, if it's not accelerating, if it's moving at a constant velocity, or if it's stationary, there's no resultant force applied on the object. That's the first law. So he's got a big mix here of a lot of ideas. Now, what do they say on the corrections? Here they have a little bit of a talk before the question, saying candidates usually, although not always, spotted that the equal and opposite forces should refer to Newton's third law and linked the balanced forces correctly with Newton's first law, or sometimes the second law as an acceptable alternative. It says some candidates stopped there, but many spotted the 3 marks and looked for something else. So after having answered those two, they were still looking for a third one. In any case, they only altered "nothing can move" to an explanation that objects have no acceleration or remain at rest or in uniform motion in a straight line. That was done relatively rarely. So this indicated that these candidates assumed that if forces are balanced, an object must be stationary. Some altered the final part to say that the object is in equilibrium, but this was insufficient as it is equivalent to having balanced forces. So let's have a look at what they've answered here. The force of weight pulls the bottle down. The bottle pushes down on the table. So by Newton's third law, the table pushes up with an equal and opposite force. According to Newton's first law, if the forces are balanced, nothing can move. So that last statement is incorrect, because things can move perfectly fine if the forces are balanced, they just do not accelerate. Let's see what the examiner says. In this response, the references to Newton's third and first law are correct, which I agree, for 2 marks, but the third category was to substitute weight for gravity, and "nothing can move" has not been corrected. So he corrected a couple of ideas, but not all of them. And it's interesting there that it says that it forgot to neglect to change weight for gravity, and that is interesting, because he says the force of gravity pulls the bottle down, and he said the force of weight, which is a strange thing. That's what the student did. He substituted those two words, hoping that would be the third mark, but it wasn't. Hopefully there's a better answer now here. It says the force of gravity pulls the bottle down. The bottle pushes down on the table, so by Newton's third law, the table pushes up with an equal and opposite force. That's all correct. According to Newton's first law, the resultant force in the bottle is zero. It will either remain stationary or continue moving at a constant speed. And as the speed is initially zero, the bottle will remain stationary. That is an absolutely excellent answer, and well, I'm sure it was awarded all the marks. Let's have a look at the next question. Says in 2008 a new energy scheme opened on the Scottish island of Eigg. The scheme uses solar, hydroelectric and wind energy. There are also standby diesel generators. In a feasibility study, the following information was collected about one possible hydroelectric site. So this is going to be about energy and rate and power and work done and all of those kinds of things, so that should be already sparking in our mind. So let's see what this is saying. It says the mean rate of water flow into the turbine is that much, meters cubed per second, so that's a quantity of volume per second, right? Meters cubed per second. So if we knew, that's a volume, so if we knew the density, we could know how much mass is going in there, for example. Okay, so that's a volume per second, and then it says the change in the height of water was 30 meters. Okay, the first part says show that the power available to the turbine is about 40 kilowatts. And here they go, they give us the density of water, which we should know anyway, 1000 kilos per meter cubed. It's one, yeah, anyway, okay, so what to do here then? So the amount of energy that the water has, gravitational, right, which here it's losing 30 meters, is going to be related to the amount of power available, and the maximum power available for the turbine will be the rate of loss of gravitational energy of the water. I hope you can see that the water is over here. So what's the question number? 16. So in question 16 we have a lot of water up here, and it's falling at a certain rate, and there's a generator and it falls 30 meters, and they tell us the speed of flow of the water, right? Let's see what they give us. 0.13 meters cubed per second, and they give us the density of water, and they ask for the maximum power. So the maximum power, if we need to realize that the energy is being transferred by the potential energy. This guy over there has a certain amount of mgh, and the rate, the change in mgh is going to be equal to the change in energy supplied to the turbine, right? And we want the power, so we want the energy divided by the time, so we need to know the changing potential energy with time. So they give us, so let's find out how much, since they're asking us for the power per second, and here we have how much volume per second, so let's limit the whole problem to 1 second, and then if we find out how much potential energy, mgh, is converted in 1 second, then we will have the power, right? So 0.13 meters cubed means that if I multiply that volume, 0.13, right, volume times density is equal to mass, and I need mass for my mgh. So if I say that 0.13 times 1000 kilos, which is for 1 meter cubed, and this is 0.13 meters cubed, so I multiply those two together, I will have, well, decimal point moves 3 times, so I'm gonna have 130 kilograms of water passing every second. Okay, so if I calculate how much potential energy that's going to lose over a drop of 30, actually, that's, let me think. Yes, it drops 30 meters. That's how much it drops into going to the turbine. So that's fine to assume that that's the height change. So what do we do here? MGH, we have 130 times 9.81 times 30 meters will give us the amount of joules per second, and therefore the power. And so we need to show that that is roughly around 40. So I'm going to get my calculator and see if I get a similar number there. So I just did that in the calculator and I get 38,259 joules per second. So 38,000, that's close to 40, and okay, you can do it like that also, like the guy is done here. You round it to 39,000 watts and you say that's approximately equal to 40 kilowatts, and showed. It says let's see what the examiner says. So the response shows an appreciation of the relevance of gravitational potential energy and quotes the formula, but does not substitute the correct values needed to gain this mark. It includes a product of density and volume, but shows no appreciation that this is mass, and does not get this mark. Finally, the candidate is satisfied that 3,900 watts is close to 40 kilowatts and does not take advantage of the show that value given as an indicator that they need to try again. And I had not noticed, but his answer is actually wrong. He's got 3,900 watts, and it should be, that's not 40 kilowatts, that's nowhere near, that's like nearly 4 kilowatts. So he's out. Right, and yeah, you can see here he did 0.13, but he didn't calculate, he didn't multiply, he just took the volume. He didn't multiply by the density to give the no, actually he's got here the density, so he missed, I don't know, he missed a factor of 10 somewhere, not very sure where. But he's going to miss marks for that vagueness, basically. That's it. It doesn't have G, right? It hasn't included 9.81 in the calculation. That's where roughly his 10 out of a factor of 10 out of that comes. And he didn't make a specific statement saying that mass is volume times density. So he didn't calculate M separately and then include that into the other place. So his working is not very good there either, so he won't get any marks for that. Hopefully that analysis makes sense to you. And here's a different guy who presumably did it better. And yeah, look, mass is equal to rho v. His rho is not very good, but anyway, rho v. Multiplies them, gets the mass, 130 kilos. Then puts it in here and says, well, power is energy divided by time, and the work divided by time, and the work done by the water as it falls down is mg delta h. It's an interesting way of doing it also. Instead of potential energy, he did it with force times distance. Force is mg, the weight of the water, and the distance is the change in height. So he did it in this way and he got the answer, and then left 38.3 kilowatts, which is roughly equal to 40. So it's an interesting way of doing it there. Instead of using mgh for potential energy, he uses work done, and that gets full marks. So that's a very good answer. Hopefully you can see the difference between that one and the other one. It's much more clearly laid out and it doesn't make any mistakes thanks to not having tried to do everything in one go. The next part says, study suggests the typical output for the turbine might be only 6 kilowatts. Suggest a reason for this inefficiency. There's a whole bunch of them, and hopefully you can come up with one of your own. But we're going to have a look at what they're writing, just in case we can get some insight from there, from looking at other people's answers. Heat lost as thermal energy, hence reducing the efficiency. And it says, look for this, it's interesting, it's for 1 mark only, and the examiner says this response does not obtain the mark because there is no suggestion of why there is any heat involved in this water flowing through the turbine. And that's true, it doesn't explain why just heat loss. That's a GCSE mark, but it's not an A-level mark, I'm afraid, and it's good that he makes this clear here. Hopefully this is giving you a very clear idea of the level of detail you need to be answering the questions at, and most of them don't require more knowledge of physics than you already have. It's just much more care in how you express yourself. So look at this, it says not all of the gravitational potential will be converted to electricity. Some may be lost, or some may be used as heat due to friction in the machines, for example. And this gets the mark because it says the cause of the generated heat. As simple as that. It's not more fancy English than the other one, it's just more properly explained. Well, I think I'm running out of time for this video, so I'll do the next question, or the next part of this question. Actually, this is part B. Yeah, I'm just going to continue and try to be brief in this part, so at least we can finish this whole question. Since the whole project involves one 100 kilowatt hydroelectric system, 2 smaller 6 kilowatt hydroelectric systems, a 24 kilowatt wind farm, and a 10 kilowatt solar energy system. There are also 2 80 kilowatt diesel generators on standby. That's on a publicity scheme. And it says calculate the maximum energy output from the solar energy system for a period of 6 hours. Okay, so maximum energy output, and the solar system had 10 kilowatt solar energy system, so this is in 6 hours. So we do part 1, we do 6 hours, which is 6 times 60 minutes times 60 seconds is equal to however many seconds. Then we have that it's 10 kilowatts, so that's 10 times 10 to the 3 watts, that's joules per second, and that's for how many seconds it's going to operate, right? And it's 10 kilowatts, so we can multiply those two numbers and get an answer for the total as a maximum. Okay. Yeah, this one didn't convert, the answer of the guy didn't convert it into time to seconds, so he missed that mark, but the other answer is proper, so he writes there the maximum output. Should have used standard form there, but they won't lose a mark for that because it uses they could lose a significant figures mark because everything he's given is into significant figures, but they're okay with him there, so they give him the 2 marks. The next part says to discuss the suitability of the output of the standby diesel generators. So discuss the suitability, so how suitable the output of the standby diesel generators is. It says there are also 2 80 kilowatt diesel generators on standby. So the idea there would be to these are standby guys, so they're supposed to kick in when the others are not working. In other words, they're asking you to add all of these, which are 100 plus 6 plus 24 plus 10, which would be 140 kilowatts, and compare it with 2 of these guys, which is 160. So 160 is more than 140, and therefore the diesel generators are enough to substitute the other systems in case something went wrong with all the others. So that's what they're trying to get you to get at, basically. And if we look at the answers of the person here, they say in the first one energy is 146, so it added those, and then that the diesel generators is 160, so that's fine, and then there would be wasted energy, so that they are not suitable. Wasted energy. That's not the right approach to answering it, I'm afraid, and I think the guy will say that here. This response calculates the power outputs correctly but does not draw the correct conclusion and is only awarded first mark. So that's the wrong conclusion. The second guy says it better, I'm guessing, and it says maximum power of diesel generators is 160, maximum power of the renewable systems is 146, therefore the diesel generators will produce more than enough power to cover the other systems in the event of them failing, although burning diesel releases CO2. So a nice environmental comment there to finish on, and got the 2 extra marks, even though that they stated that extra thing and it wasn't necessary. It says here that it does not affect the mark. Okay, so we'll see you in the next video for the next few questions, and until then, take care.